welcome to the Maths Advanced lecture in the January 2023 series. My name is Krisha and I'll be taking the lecture today. So before we properly get started, I just wanted to thank everyone for joining in today, and a big thanks to our university sponsors, because without them, this series wouldn't be existing. Now, if you do have any questions that could be related to Year 12, Maths, Advanced, Extension 1, Uni, anything, life, make sure you pop it in the chat, the Slido poll just below. I've also just opened a welcome survey, just got a couple questions just to get us on a bit of a roll. Now, at the end of each session, I think we've just got 2 blocks today. So at the end of each block, we'll have a Q&A session just dedicated to answering your questions. And if you see on the Slido polls, or Slido Q&A, if there's someone that has a similar question to you or one that you would like to be answered, just give it a thumbs up, I think it is, just to upvote it. So the higher the vote is, the higher it gets onto the chart, so the faster I get to responding to it. And also, while we're on the topic of the Q&A, while I go through all of the questions, I do have Slido right over here on my second screen. So if I'm going through something and I make a silly mistake, because I'm very prone to it, or if I am going through something and you just don't quite understand something, can you go back to slide 43? Can you go check this? Can you explain this a bit further? Pop it over there. I'll see it straight away, and I'll stop myself in my tracks and just go back to answering your questions, okay? Now, before we get started, I'll just start off with introducing myself. My name is Krisha, as I said. I graduated 2 years ago now in 2021. I received an ATAR of 95.85. I did Advanced Math, Extension 1, Physics, Chemistry, DT, and English. Currently, I'm just about to go into my second year of uni at UCID. I study veterinary biology and veterinary medicine. And a bit about me as a person, you can see already with my university degree, I am a huge animal lover. I am always rescuing or fostering animals. And if you do, we'll speak about ChooseSmart a bit later, but if you do join my tutoring class, you will hopefully see some cameos of some of my fostering kittens. Another thing about me is that I like rock climbing. It's something that I've just recently gotten into, and I can't say that I'm very good at it at all, but I really do enjoy it. And another fact about me is that I am a responder for St. John Ambulance. Yeah. Okay. In terms of ATAR Notes, this is my 4th lecture series with ATAR Notes. I just finished the prelim math lecture, and after this, you guys can join me in the Smash HSC if you'd like. You can also find me next Tuesday for the in-person math lecture. I think that's like $5 in UTS. Definitely worth it though. And then on Wednesday, I'm doing the chemistry in the morning as well. So yeah, as well as that, I am, as I said before, the Maths Advanced tutor for TuteSmart. So I really recommend you joining. So it's just me with a group of students, possibly also you in the future. And if you have any specific questions, or if you're struggling with any topics, I can source and create specific resources to make sure that you achieve your specific goals. So I really would recommend, but I'll go into that a bit later. So before we properly get started, I'll just introduce ATAR Notes a little bit. So ATAR Notes started in 2007, and we had our little forums and our website and stuff, and we really became big in 2015 when we started our holiday lecture series. All of our holiday lecture series have been for free. In 2020, we moved to online from UTS, and that made us somehow even bigger. And now, as of I think July holidays last year, we've started to slowly go back to the in-person lectures. I think we'll be keeping the online lectures because we're able to reach more people all around New South Wales. But yes, we've just started. They're not free, the in-person ones at the moment. They're $5 per person, but would highly recommend. Now, a bit more about ATAR Notes is that our mission is to reach and help as many students as possible. So we have a range of free resources, including study notes, the lectures that you're at right now, the community discussions and the forums. We have videos, the newsletters that you can sign up to with your email, as well as the articles. And probably our most popular is our ATAR calculator. Now, if all of those combined isn't enough, we also have a bit more. So we have our own low-cost tutoring system. It's called TuteSmart. So we have our group tutoring and our private tutoring. I'm one of the tutors from TuteSmart, as I've already said. We've got our study guides and our Ed Unlimited. I'll go into all of those a bit later, but this is just everything that ATAR Notes offers. So for today, we'll be picking up where we left off in the September lecture. Okay, for those of you that didn't get the go to the September lecture, I think you can go onto the website, and I think possibly in the top right corner there will be like a button that you can press to see previous lectures. But we will be going through a little quick recap as well, and we'll be going a bit further with optimization and integration as well. Okay. And then, if time allows at the end, we'll get started with a little bit of statistical analysis as well. Okay, so before we properly get started, I'm just going to get everyone to fill out the poll that I've got just beneath, just the intro poll, and I'll just start presenting that. Okay, let me see how we're going. Okay, we have a range of people here today. Okay, a lot of people are alive. I'm happy to hear that. Quite a few people living, loving, and thriving, which is amazing. I'm hoping the holidays has really rejuvenated a lot of you guys. Got a couple of zombies, that's okay. 10% of us are struggling. I hope this 22% of us are feeling okay, and that, you know, we spend the rest of the holidays trying to make ourselves feel a bit better so that we can, you know, not get more burnt out than we already are as we move through to the remainder of year 12. Okay, and a few of us still rocking the holiday spirit. Yes, that's me as well at the moment. Okay, now how are we feeling now that we're already done with a quarter of year 12? Okay, a lot of scareds, terrifieds, nervous, stress. I like this one. Great, nice. Got some emojis. Can't wait to be done. Yeah, that was me as well. Yeah, so we have a massive range of emotions, and that's okay. We've got quite a few happy people, which is nice to see as well. But insanely excited, but dreading the stress of, yeah, definitely. Now I added this poll here not to like stress you out and be like, oh my gosh, you're already done with a quarter of your year 12. It's just there to tell you that, number one, you're already done with a quarter of year 12, and I mean that in the best possible way. You're already, so here's the curve, you're already here, just a little bit more, and then it's all downhill from there, okay? And for those of you that that aren't super confident with yourselves right now, that's okay. You've still got 3 more terms to really lift yourself up, change yourself, turn yourself around if you're not doing too well, and you can still get whatever mark you're aiming for plus, okay? And now, how would we rate our holiday so far? Oh, I like this. I love this. Okay, lots of people are happy with their holidays. And then I'm guessing this is like one person is not very happy with their holidays, but it wasn't terrible, which is not bad at all. Okay, it's good. Good that you guys have been enjoying this holidays. Okay. Now let's move on to today's lecture. Okay, so the plan for today is we're going to start with differential calculus, then we'll have a little bit of a dip into integral calculus, then we'll take a break, continue into integral calculus, and then if time allows, then we'll add statistic analysis. Now, this is not at all my priority today because if you guys would like me to go slowly and get everything done at a good pace, I'm more than happy to just break it into two parts, being differential calculus and integral calculus. I don't mind at all, okay? We'll see how we're going with time, and then I'll put up a poll for like how the pace is going a bit later, and then we'll go from there. Okay, so topics that we'll be covering today is calculus, the whole of it, and then if time allows, this second half of statistics. Okay, next time we will be going through functions, which is a nice topic. I think it's a bit of a rest. And then financial maths, which some people, it's the bane of your existence. Some of you guys, it's the love of your life. For me, it was a bit of both. Okay, so before we properly get started, I just want to see what everyone's already done in school. So I've got another Slido poll just to fill out what topics have you already covered at school. I'm just curious to see who's done integration. So yeah, just down below in the poll. Oh, sorry, I didn't add multiple options. Sorry, I'll do it again. Sorry about that. Okay, we'll wait until maybe 40 people, and then lovely. Okay, functions, lots of people have done. Differentiation, lots of people have done. Trig functions, lots of people have done. Financial maths, quite a few people have done actually, pretty good. Stats, random variables, okay, and barely anyone's done calculus. Okay, so if that's the case, there's a high chance I might just split it into two lots, so differentiation and integration. We'll just see how time goes, okay? Okay, so let's get started with differentiation. We're going to start with the real basics. Now, what exactly does the derivative do? Graphically, the derivative just points out the gradient of the tangent of a curve at any given point. So we can see over here, we've got this curve that goes like that. At this point over here, if I were to draw a tangent just looking at the gradient of the curve, we can draw that out. And that is the derivative. That's what the derivative can help with as well. Okay. Okay. Oops. Okay, so now let's go through the actual rules. So this is the very basic rule. So the differential of x to the power of n, we bring that n down to the front, so we times it as a coefficient, and then we reduce that power by 1. Okay, so the simple one, let's say it's like 3x squared. Then if we're going to derive, it's equal to 3 times 2 times x to the 1, which is 6x. Okay, that's how we use that rule. I'm going to assume that most of us know this at the very least because it was also taught in year 11, but let me know if not. Okay, then we have the differential of trig functions. I personally don't even remember what we went through last holidays, but I do remember a lot of you guys hadn't gone through trig differentiation. But yeah, I don't think I'll have enough time to like draw the graph thing because I did that last time as well. But it's also in your formula sheet that the derivative of sine x is cos x, the derivative of cos x is negative sine x, and the derivative of tan x is sec squared x. Okay? We'll be going through a lot of formulae in the start. It won't be super duper interactive, but we just need to get all of the basics done first, okay? Now we have the exponentials. The derivative of e to the x or e to the f of x is a dupe. It's probably the first one that you guys learn apart from the actual rule itself. And that, if we're going to do it properly, it's e to the f of x. derivative of that is f dash of x times e to the f of x. Okay. Then we have this disgusting formula. I personally would not recommend you guys to memorize this because in the HSC you'll receive like 1, maximum 2 questions on it, and it's in your formula sheet and you'll rarely receive a question on it, as well as this one over here, this log one. I think I've received 2 questions on it in my life, and that was like in a textbook. Okay, so these two, know of them, know where to find them in the formula sheet. Don't worry about memorizing. This one over here though, super important to memorize. And that is the natural log of f of x is equal to f dash of x on f of x. Okay, so it's a pretty simple one, but a lot of people seem to forget it. But I want you guys to pay special attention to this, because when we start integrating, this rule, well, the inverse of this rule, is one that everyone forgets, and the HSC like waits for you to forget this. Okay. So then we have the chain rule, which looks a little something like this. So it's a function within a function, and we need to, I don't know how to explain it without a question. Let's say we have x squared plus 1 all cubed. So if we want to derive that, then we take the g, well, we'll go the f dash x first. So this is f of x inside the function. F dash of x is 2x times 3 x squared plus 1 squared. Okay, so that gives us 6x x squared plus 1 all squared. That's how it works. I personally am not too good with explaining how that one works, so sorry. Okay, then we'll just put them all together. If you wanted to take a screenshot of this, I'll give you like 5 seconds. So 5, 4, 3, 2, 1. Okay, we'll move on to the product and the quotient rule, aka the 2 rules that people always accidentally mix up together. But yes, so if we're taking the derivative of something that's being times by another like 2 separate functions, so let's say it's like 2x times e to the x, so they're 2 separate functions, then you will need to use the product rule. And then the quotient rule would be like x plus 2 on x. Or yeah, you can use the product rule for that, the quotient rule for that, sorry. So yes, I'm hoping you guys are kind of familiar with this. If not, I'll just go through a question anyway. We'll do the quotient rule because that's a bit more of a tricky one. So let's say the question is e to the x on 2x, okay? So I will say that u, which is the numerator, is equal to e to the x. V, we'll do v over here. V is equal to 2x. U dash is equal to e to the x. V dash is equal to 2. Okay? So we're going to follow that same pattern. We're going to times by this first and then minus that. So ex times 2x minus 2ex. Oops, pressing all the buttons. All on 2x squared gets us to 2x ex minus 2ex on 4x squared. We'll take out a common factor of 2 and we get ex x minus 1 on 2x squared. Okay. That is how we use the quotient rule. I'm going to assume that everyone knows how to do this because most people have done differential calculus and you did it in year 11 as well. Okay, now let's do the application of differentiation. Now, once again, what does it properly mean? The first derivative is, as I was saying before, the gradient of the tangent at any given point. Okay, So that can be given in a range of like notations. So dy dx or d dx, f dash of x or y dash. Okay, and what it actually means, if f dash of a, so at any given point, is positive, then the gradient is positive, so the graph is increasing. Okay, if it's negative, then the gradient is negative and the graph is decreasing. If it's 0, then the gradient is 0. So it's called a stationary point. Okay, stationary point. That's an important word to know if you're not too familiar with it already. Okay, then we have the second derivative. Okay, so the first derivative tells us the gradient. The second derivative tells us the concavity. Okay, so concavity is like concave up, concave down. Okay, so it's basically the rate at which the curve is increasing slash decreasing. So it's got the notation d squared y on dx squared, f double dash x or y double dash. So if f double dash a is positive, then it's concave up like a cup. And if it's negative, then it's concave down like a frown. And if it is 0, then it is a possible point of inflection. And I would like to highlight possible. Whenever we have something like that, we need to test before and after to actually show that it is a point of inflection, because sometimes it might not be. Okay, now I have a slider question for you. Okay, so just down below, let me know at which point on this curve are the first and the second derivatives both negative. I'll give you guys a few minutes. Got a couple of responses going through. I'll give you another minute. Okay, we'll wait till 40 if we can. Okay, Q. Okay, now let's show the correct answer. It's B. Good job, most of you guys. Now let's just go through this. So what does it mean for the first derivative to be negative? The gradient needs to be negative, so it needs to be decreasing. Now that takes out, well, I'll just circle which ones. So it's decreasing at B, it's decreasing at C, okay? Then it needs to be second derivative negative. So it needs to be concave down, like a frown, okay? So what does that mean exactly? You can see it a bit more clearly over here, where this is still increasing, but it's got a negative concavity. So here and here. So what like satisfies all of them? It's B. Okay. Now I was supposed to go through something, so let me quickly work it out. Okay. And now we'll just quickly draw a few things. Okay, so we have this, and then we have this, and then we have this, and then we have this. Okay, so if we take a look at the actual behavior of the curve in all of these oddly shaped pios, I don't know what they're called, you can see over here that the derivative is positive, and so is the concavity because it's concave up like a cup. Okay, over here, we're still concave up, right? So f double dash x is greater than 0. and f dash of x it's negative, so it's decreasing, right? Okay, over here we're still increasing, but it's like at a lower rate, right? So it's going concave down like a frown. Oh, sorry, increasing still, and a negative concavity. And over here, we're decreasing, and we're decreasing at an increased rate. So we're concave down like so, and with all, oopsies. Is negative, and so is this. Okay. Awesome. Okay, hopefully if anyone has any questions on this, just pop it in the Q&A. And just as I was saying, it's literally right on the slide over here. So when I'm going through, I'm always glancing and taking a look so that you guys can stop me whenever you need to. Okay, now as I was talking about, I highlighted a bit earlier, stationary points. Stationary points are when the gradient is equal to 0. It can either be a maximum turning point or a minimum turning point, or occasionally neither. There's ways to determine it. Two of them, well, yeah, there's only really two. So there's the table of values, which one of my students, like that just graduated, their school called I don't know if their school or just they call it the bucket hat test, and I like that, so I'm going to call it the bucket hat test as well. And then there's the second derivative test. And they both have their pros, they both have their cons, and we'll go through both ways just to see how everything, like what you prefer, because it's completely up to you. Okay, so we've got the table of values. Find the value of the derivative near the stationary point. So next to it, to the left, next to it, to the right. Okay, so we'll have like, obviously it'll look a bit nicer for you guys because you're not drawing on a screen. Okay, so we'll actually write proper numbers. So let's say, actually no, I won't write proper numbers, but just know that they should have proper numbers. So x, f dash of x, x, f dash of x. Actually, I'll put real numbers. 1, 2, 3, and then 4, 5, 6. Okay, just showing as an example. So we'll put this is the turning point, this is the turning point, and this is -2 plus 2, and this is +4 minus 1. Okay, then we use the bucket hat test, and we see that this is decreasing, this is stationary, and this is increasing. Therefore, min TP at x is equal to 2, right? Because it goes like this, as opposed to this, where it goes increasing, 0, decreasing. So the bucket hat is down. So therefore, max TP at x is equal to 5. Okay? Perfect. When drawing a table of values, which values should you choose? How close to the number are you testing? How close to the number you're testing do they have to be? Ideally, the closer the better. Especially like if it's a really simple curve that's only got like one stationary point and stuff like that. Sure, you can do like what I've done, like one number to the left, one number to the right. But if it's a more complex one, it's got like a few things going on, I personally would go as close as you can. So let's say like if the turning point was at 2, I might go 1.5 and 2.5. Or I could go even closer and be like 1.9 and 2.1. They're ideal, 1.9 and 2.1. They just won't be as nice of a number and a bit more difficult to put into your calculator. But ideally, best thing you can do. Get as close to 2 as you can. I hope that answers that question. And then we have another question. Can't you simply just put the stationary point into the double derivative to find the nature of it? Yes, you can. That we will go through right now. Do you have to specify if it's a local or a global min point? Pretty much no, unless the question asks for it. But your teacher might want you to do a different thing. My teacher never told me to do that. So the HSC won't tell you to do that, but maybe your school might mark differently. But yeah, it just depends on what the curve looks like. You can never go wrong by saying whether it's a local or global minimum / maximum point. But yeah, just depends on the question and your school. Okay. Next one, so we need to find the value of the second derivative. If it's positive, concave up, or minimum. If it's negative, concave down, therefore maximum. Do they have an example? No, they don't. That's so annoying. I'll just make one up. So let's say it is x squared minus 2. Okay, that is my thingy. So f of x. So f dash of x is equal to 2x. Therefore, TP at x is equal to 0. Okay, now I need to find the nature of the turning point. I could do two things. I could do the bucket hat test that I just did before, or I could find the second derivative. So f double dash x will just be equal to 2. Okay, so at any given time, it is a positive concavity. Therefore, min TP at x is equal to 0. Okay, that's how that works. We'll go through more questions like that in the near future. Okay. Recall the points of inflection are where the concavity changes. Sometimes they could possibly be a stationary point as well. Think of like a cubic curve. So like this. Like this, it's got a horizontal point of inflection, it's called, if there is a stationary point and a point of inflection. So over here it's concave up, over here it's concave down. Or it could just be something like, oh, why is it so hard to think of one? Like that, literally like that. So right here is the point of inflection. On the left of it, it's concave up. On the right of it, it's concave down, okay? Stuff like that. That is a concavity change. But any given like time that you like, I can't speak today, sorry. Anytime that you are looking for a concavity change, you do need to use the bucket hat test to figure out whether it actually is a concavity change, because sometimes it could be neither. Okay, so I'll show you some examples. So we have a concavity change. Looks like this. Okay, that's one. This is the other. And this is the other. Okay, so over here, we'll just write d squared y dx squared. So here's the point of concavity, here's the change of concavity, and here's the change of concavity. Okay, so initially we have a negative, a 0, and a positive concavity. Over here we have a positive, a 0, and a negative concavity. And over here, it's a bit of a special one. It's a positive, a 0, and a positive. Okay, so, oh, sorry, this is negative. So because there is a change in concavity in this one, it goes from negative to positive, therefore POI. Over here, there's also a change in direction, right? It goes from positive to negative, therefore POI. And over here, at that given point, the concavity is 0. However, there's no change in concavity. So therefore, there is no POI. Okay? Okay. Note that when doing a question, you should write the actual values. Yeah, so like I said over here, well, like I did over here, I did minus 0 plus. Minus 0 plus is not really what we should do. We should put proper numbers, just like I did over here. Put proper numbers in, and then put proper numbers into the answer over here as well. Otherwise, you're probably going to lose a mark. Okay. Yes, so we'll use an example. Like so. So this is x, so f double dash of x, and we have 1.9, 2, and 2.1. Okay, and I've just made up some random numbers: 0.12, 0, negative 0.12. Okay, so this is concave up, this is 0, and this is concave down. Okay, so therefore we can say, and like this is for an example where we're testing stationary point at x is equal to 2. And yeah, so this is just a scenario, by the way. I'm not using any specific numbers. But then you'll say, therefore, max t. I am so sorry. I don't know what I'm doing. This is supposed to be a derivative question, and I am not doing it. I am so sorry. It's supposed to look like this. It's a derivative question, not a concavity question. So max TP at x is equal to 2. Okay, sorry. I've just got like random notes on my side piece of paper, and I did not write them too well. Okay, then we have if a stationary point happens to be a point of inflection as well. As I was saying before, it's a horizontal point of inflection. And I'm going to draw a nice Venn diagram to kind of put it all together. One circle, another circle. Now this is dy dx is equal to 0, and this is d squared y dx squared is equal to 0. Okay, so this is a concavity change, not like that quartic that I had in the previous slide. Okay, so this is a point of inflection. This is a stationary point. And when we put them together, and it's both a stationary point and a point of inflection, it is a HPOI, aka a horizontal point of inflection. Oh, it is really hot today. Okay. Yeah, so just over here, this would be a horizontal point of inflection. Okay. Yes, so all of this is useful for curve sketching, and we will go through that not today, but in the next lecture series where we put together our differentiation skills, integration skills, put it all together with our graphing skills, and we throw it onto a piece of paper. That's all for next time. But we can apply differentiation to go further than just curve sketching, okay? And we can use it for problem solving, okay? So let's go through a question right now. Okay, so a farmer wishes to make a rectangular enclosure of area 720 meters squared. She uses an existing straight boundary as one side of the enclosure. She uses wire fencing for the remaining 3 sides, and also to divide the enclosure into 4 equal rectangular squares of width x meters, as shown. We're given the total length of wire fencing, and we need to find the minimum length of wire required, showing why it's a minimum length. Okay, I'm going to give everyone 5 minutes to try this on their own first. It's not a Slido question, but I do want you to just take a while to think about this. Yeah, so 44 past, we'll go through it properly. Also, we've got some really good questions in the Q&A. Make sure once you're done with the question. If you do have any questions, pop it in the Q&A or just read through them and upvote the ones that you think are good. Okay, one more minute. Okay, let's get started. So this question's fairly simple because they've pretty much given a lot of the working for us really, really nicely. We just need to find the minimum length required. Okay, so let's start going through this now. Okay, so given that L is equal to 5x plus 720 on x, we can find dl dx. Okay. Actually, let me just first rewrite this to make it a bit easier for differentiation for those of you that aren't too confident yet. So it's plus 720x to the minus 1. Okay, so something on x is the same as x to the minus 1. Okay, dl dx will be equal to 5 plus 720 times, so we're going to take that down to the bottom, so minus 1 times x to the minus 2. Okay, so it'll be 5 minus 720 on x squared. Okay, now we want to make this equal to 0 because we need to find a turning point if we're looking for the minimum length. Okay, so we're going to say that 5 is equal to 720 on x squared. I'm going to times everything by x squared and divide everything by 5, aka switch. I need a sneeze, but I don't need a sneeze. Okay, switch to 5 and the x squared. So x squared is equal to 720 on 5, which my brain can't comprehend right now in holiday mode. It's 144. Now, yes, the answer to x is 12, but we first need to write that x is equal to plus minus 12. Okay, the reason being is because we all know by now, or at least we should all know by now, that we can square a negative number and get 144. Well, negative 12 and get 144. We can square 12 and get 144. So when we square root it, we can get plus minus, right? So we then need to say, as length is less than or is greater than or equal to 0, therefore x is equal to 12 is the answer. Okay, but you need to write this because there's a chance that your like exam would have this and you might lose a mark for it. Okay, now that is not the final answer though. That's just the value of x. We now need to find the final length. So we're going to sub, go away. Okay, sub x is equal, not 5 to 12. Okay, so L is equal to 5 times 12 plus 720 on 12, which is 5 times 12 plus 720 on 12, which is 120 meters. Okay, do I just leave it there? Unfortunately not. I also need to figure out whether it's actually a minimum. What if it's a maximum? I don't really know. So you have two choices. You can find the second derivative and work from there. Now, I just don't like differentiating all of these like negative powers. It's not a bad idea. You most definitely can. But I personally would rather just do the bucket hat test. So I'm going to do the bucket hat test, okay? This is going to save me time, at least for me. So x, f dash of x, and we will sub in 12, 11, 13, something like that. Okay, so we know that this is 0, but I'm going to check anyway, just in case. So 5 times 12 plus 720 on 12. Oops, wrong. I need to put it into the derivative. Derivative is 5 plus 720 on 12 squared, which is wrong because I need to minus it. Okay, 5 minus 720 on 12 squared is 0. Now we're going to substitute 11 instead of 12, and that is minus 115 on 121. And then we have to substitute for 13, which is 125 on 169. So it decreases and then it increases. So therefore we can say, therefore min at L is equal to 120 meters. Okay? Or we should probably write a full sentence because this whole thing's a bit of a wordy thing. So then we can say, therefore, the minimum length required is 120 meters. Okay? Anyone else get that completely wrong? Let me know if I just got that completely wrong, because there's a chance. But yeah, if anyone else did get a different answer, please let me know. Okay. Now we're going to start with our integration. Okay, So I think most people, including like year 10 students who are like interested in integration, would know that integration is the opposite process of differentiation. So it's also known as finding the antiderivative. And to all you fancy schmancy people out there, it's known as the primitive function. Okay. If f of x is like the function that's given and we need to find the integral of it, then we notate that as big F of x, okay? And the integral symbol is this weird S, which I personally really struggle with drawing on a screen or on paper as well. Like occasionally it'll look really nice, but a lot of the times it looks kind of ugly. Okay. Okay, so there's two different kinds of integrals. The first one that we'll go through is the indefinite integral. Okay, so it's not set between two bounds. It's just a function, and we're just going to integrate the function and find the reverse of the differentiation. Okay. Then we have the definite integrals. Definite integrals are really useful when we're trying to find the area bound between two limits. Okay. That's pretty much it. And the indefinite integral just has this weird S. And the definite integral, when we have those two bounds, we'll write between A and B, whatever that A and B might be. Okay, those two limits. Okay, let's continue on. So when we differentiate, we need to remember that, like, let's say even in the example of like, there's examples here. So when we differentiate any constant, it becomes zero. It gets taken out of the equation for the differential. So when we integrate, we need to somehow bring that back in, which means there's a family of answers which can be shown with this arbitrary constant called c. Okay, so when we integrate something, let's say 2x, I'll go through how to integrate in a sec, but it'll become x squared, and then we throw on a plus c. Okay, every single time you need to add a plus c. It's one of the biggest mistakes, as well as like more common than forgetting the quotient and the product rule together. Forgetting the plus c, instant loss of marks, and it's really annoying. Okay. So let's start with the basics of integration. Now, a lot of us, let me go back to that poll. A lot of us have not done integration. Let me show. How do I go back to the results? Oh, that's a bit annoying. I don't know how to. That's okay. I just remember that a lot of us did not go through it. So I'll go through this really nice and slowly, okay? Yeah. So let's get started. So just as when we differentiate like x to the n, we get n times x to the n minus 1, right? Now we're going to do the complete opposite. So I'll write it here. So dx xn is equal to nxn minus 1, okay? Now we're going to do the complete opposite. So to reverse that whole thing, I need to, number one, increase the power instead of subtract the power like I did over there. So I'm going to increase by 1, add 1 instead of subtract 1. And then, because I times this down the bottom, I need to divide, okay? So it's going to be x to the n plus 1 all on n plus 1. And because it's an indefinite integral, I need to chuck a plus c. Okay, this is on your formula sheet, and I just need to check, is it actually? Yeah, it is. It's just got a bit more fancy terms. I want to go through this with you guys on the formula sheet as well. All right, page 3, right-hand side. It's the very first one, okay? So it's a bit more fancy terminology, exact same thing. I personally would like for you guys, if you're going to like familiarize yourself with anything, this is the one to familiarize with, because it's used a lot more openly than just x to the n. Okay, so let's go through this one as well then. So if we have any function to the power of n, then we need to also have the derivative out the front because we're doing the antiderivative, right? So we need to have, it's kind of like the reverse chain rule. So we bring that back in, and then we times by 1 on n plus 1, and then increase the power by 1 as well. Now it sounds really complicated, but I promise you it's a lot easier than what I'm saying. Okay, and now what happens if we have 1 on x? So if n is minus 1, then I think you will recall me saying that to take really, really good caution of the derivative of ln x. If you remember what I said that it's 1 on x, right? The derivative of ln x. And that's because a lot of people get stumped by looking at the integral of 1 on x. And it's just the antiderivative of that. So more importantly, let's go back to the formula sheet. Let's take a look at this equation. Exact same thing over here. So the integral of the f dash of x on f of x will get us ln of the function all plus c. Okay? Okay, then we have our trig functions. So just as the derivative of sine x gets us cos x, the integral of cos x gets us sine x. Integral of sine x gets us negative cos x, and integral of sec squared x gets us tan x. Now, I think it's super important that we take a look at the signs, because another fatal flaw of many HSC students, I personally can say that in a lot of my textbook homework exercises, I'd always stuff it up as well. Just the signs, so the negatives, the plus, the positives, and that's because you just get a bit overwhelmed by the differentials and then the integrals, and then when you differentiate cos, it gets minus sign, but this time when you integrate cos, you get positive sign. So while you're still learning and while you're still going over your textbook and stuff, once you do get to this, I think it's super important for you to just go back to your formula sheet, make sure that you're doing the right sign, like the positive or the negative, and just be conscious of that, because that's one of the big silly mistake slip-ups that you can definitely have. Okay. Now we have the exponentials. We have e to the x, similarly gets us e to the x plus c, or better yet, because I don't know why we've made it a bit more simple, but if we have the derivative of that exponential function times e to the f of x, it gets us to e to the f of x plus c. Okay, and then this one over here, just like how I wouldn't bother memorizing the derivative of this in differentiation, I wouldn't bother memorizing the integral of this either, because it's on our formula sheet already, and I don't think I've received many questions on this at all. Okay. We're going to get to a question in a sec, but just a little bit longer. So those were just the base forms. So just as I was saying before, we have other functions as well, like functions within functions. So the reverse process that we actually use is known as the reverse chain rule. So if there's a function within a function, then you'll see in pretty much all of these, we need the derivative of the function on the outside. Yeah, so that is the reverse chain rule. So the main form that you'll get your integration will be as a reverse chain rule integration. Okay, so if you're not super confident with your chain rule, I think I saw a question about what you should do in the next 2 weeks. Getting confident in the chain rule should definitely be one of those things. Okay. Okay. Now this is everything that the reverse chain rule has. If you wanted to take a screenshot of that, you can. If not, then it's a lot of the things in the formula sheet on the page 3 right-hand side. You'll see it all. But yeah, we will move on to a Slido question. Okay, I've just put it up. So the question is, what is the integral of x plus 4 all on x squared plus 8x? Okay. take a minute to think about this. Have your formula sheet on hand or on Google and get that to help you, because it's definitely a tricky one, especially if you are yet to have done integration. Okay, some of the answers are coming through. If you still haven't gotten it, that's okay. I'll give you a few more minutes. Take your time. Okay, I'll give you one more minute and then we'll start going through everything. Okay, let's get started. We've got quite a few responses already. How about I'll start going through it. Once you've gotten the kickstart that you needed from me, try and like just mute me and try and go through it yourself, but I will continue going through. Okay, so this one is a tricky one, and it's one formula that I have tried to emphasize the most so far. But let's try and like see how we can approach this question before I like throw in the formula and say this is how you do it. So just looking at this, one way that we could think is maybe we can like simplify the fraction. Maybe we can go x on x squared plus 8x plus 4 on x squared plus 8x, right? And then we'll like take out the x over here, so it's 1 on x plus 8 plus 4 on x squared plus 8x. Still doesn't help me because I've still got this disgusting stuff happening. So it's not good enough for me. I can't simplify this. Then I'm taking a look and there's an x on both sides and there's like kind of a little bit of a similar pattern going on. So I'm going to take a look at the denominator first. The denominator, I'm going to call that f of x. It's equal to x squared plus 8x. And then I'm going to take a look at the derivative of that. So f dash of x is equal to 2x plus 8. Okay, now as I look at the derivative of that, I'm taking a look at the numerator and it looks gosh darn similar. If I were to times 2 over here and then throw a half up the front, which I'll go through in a sec, it'll look the same, right? That's the derivative on the original formula. And what's the integral of the derivative on f of x? Is it not the ln formula? Is it not this one right here? It is. So we've just run into a problem though. So I need to times this by 2. But I can't just like times something by 2. Like I can't just get numbers out of thin air. The way that I can fix this is if I just times by a half on the side. Okay, so it's like timesing by 2, but then if I times by a half times 2, I'm timesing the whole thing by just 1. So it just cancels itself out. So to get the final answer, it will be a half ln, and then let's go back to the formula. It's just ln of fx in absolute value brackets plus c. Okay, so x squared plus 8x plus c. And that is my final answer. Okay, I hope that makes sense to everyone. And good job, because a lot of you guys got that right, like within 3 minutes, which is really good. I'm going to assume that most of it is. With the person that says, can you do the differentiation question proving with the second derivative? Was that for when I was discussing this over here? Can you just put like yes or no on the chat? And if it's no, then can you let me know what you did mean? Okay. Meanwhile, I will just continue with my book of mistakes discussion. I would recommend a book of mistakes. If you like a book of mistakes, for those of you that aren't too sure what they are, it's just a book. So like this, where if you make a mistake, then you will write down what the question was, what you did wrong, and if you can, why you got it wrong, and better yet, how you can fix it for the future. Okay, just those 4 steps for every question that you get wrong, including like textbook exercises, even small things, all the way to like topic tests. Okay. No, the farm area question. Perfect. Okay, I will go through that right now. Farm area question. This one right here. You can definitely. I will go through it right now. Okay. So dl dx is equal to 5 minus 720 to the minus 2, right? So d squared L on dx squared is equal to minus 720 times minus 2x to the minus 3, okay? So it's 720 times 2. Yeah, and then that's it. And then you can just sub right into there. So f double dash 120 is 1440 on 120 cubed, which is 1 on 1200, which is positive, therefore concave up, therefore min TP. So yeah, works the same way. That one wasn't too bad, but yeah, when you get to more disgusting equations that need the product and the quotient rule again, when you differentiate, they're the ones where I recommend the bucket hat test, just because it will make your life easier, and as I was saying before, it's less likely to make a mistake. Okay, cool. Let's continue on. So before we properly get started with the second half, I just wanted to talk about Ed Unlimited and our bookshop. So Ed Unlimited, if you've been to any of our previous lectures, you'd know that we call it like the Netflix of the HSC. It has a massive range of resources for you, including like topic tests, notes. We've recently like partnered with Neep, who makes like pretty awesome like trial exams that like schools actually buy from them. So that's really good. And then text guides as well for all you people. Well, everyone does English that needs texts. Ed Unlimited has them, and I personally used them during my HSC, and they were really, really helpful. Yeah, and then we've also got like the subject notes as well. So if you're interested in like applying, or if you just wanted to try for 21 days for free, then you could try my code. It's Krisha HSC. So in the next 2-ish weeks that you've got for like the holidays, and if you're looking to, you know, smash out some stuff and like get ahead, or as I was saying before, practice on that year 11 content or the previous content so that you're properly ready to get started with the year. Ed Unlimited is honestly like your one-stop shop. It has literally everything you need. Okay? And I say this as I was a previous TuteSmart student, and I had Ed Unlimited and everything, and I personally can say, like, as a student, not as a tutor, that it is one of the best, like, purchases, would you call it? Subscriptions, like resources that I've used. Okay? And then if you're not too much of like the online like book kind of person, we've still got you. We've got a discount for our like bookshops. So 15% off if you just put in the code at checkout, 15 Jan. These all expire on the 31st of January. So for if you wanted to try the free 21 days, even like all the way up till the 31st of January, if you put it in, then you'll get 21 days from that day onwards. Okay. Now let's continue on to more integration. So as I was talking about earlier, when I was talking about definite and the indefinite integrals, we've gone through the definite integrals now. We just need to now go into the definite integrals, which are the ones that I suppose we use more. So it's used to find the area bound by the curve and two limits. Okay. Another thing to point out is when we take the integral, like mathematically, we need to take account for the fact that when something is below the x-axis, you are getting a negative integral. Okay. Why am I saying this? It's because when the question on the paper says what is the area bound by the curve between A and B, instead of what is the integral of this curve between A and B, two different things, integral and area. If I wanted the integral between A and B, I'll just integrate the whole thing between A and B. If I wanted the area between A and B, then I would unfortunately need to separate it into three different things. I'd go between A and, we'll call this one B instead, okay? And then between B and C, and then between C and D. And what I would need to do is I would need to find the integral between A and B of f of x. Okay, And then I would need to find the integral of b and c of f of x, and then I would need to find the integral of c and d of f of x. And more importantly, this b and c part, oh no, don't do that. I would need to find the absolute value of it. Now, the reason why I need to find the absolute value of it is because it would give me a negative integral. So I need to find just the area. Okay, so if I'm just trying to find the actual value given the like the numbers here, then then dx, a and b is 4, b and c is -3 without the absolute values, and the integral between c and d is 2. Okay, so if I wanted the integral between a and d of f of x, then it will be 4 minus 3 plus 2, which is 3. But if I want the area, then I need 4 plus absolute value of -3 plus 2, which is 9. See, you can see that there's a massive difference between 3 and 9, right? Yeah, so that is how we do it. Okay, what if the whole area is negative? Does that mean the area is negative? Okay, now I hope you guys are familiar with the idea of vector versus scalar. If not, don't worry, it's more of a physics thing, but it's basically area is something, just like length, you can't have negative length. In the same way, you can't have negative area. Area can only be like an absolute value kind of thing. So if the whole thing, so the person that asked was, what if the whole area is negative? Does that mean the area is negative? So let's get one note out. So here's my thing, and the whole curve is like that, and I just want the area between here and here. Now, while it all is negative, I could take the integral between a and b, but I would need to take the absolute value of it because there's no such thing as a negative area. It's just area, okay? So you just make it the positive sign. Oh, all good, all good. Just in case no one else understood, it's important to know. Perfect. Okay. So we evaluate definite integral signs by using the second fundamental theorem of calculus. Okay, so that is that the integral between a and b of a function is the integral like value of b minus the integral value of a. Now this might mean absolutely nothing to you right now, which is okay, which is why we'll go through a question right now. So evaluate the integral between -1 and 2 of x cubed dx. Okay, so let me do this down here. Actually, no. Do I have enough space? I don't. I'll quickly take a screenshot. Okie dokes. Okay, so just the integral, I'm going to follow that rule that I just said. Okay, so the integral between a and b of f of x is equal to primitive b minus primitive a. Okay, so let's show the full working. So the integral between -1 and 2 of x cubed dx. Now what I'm going to do is I'm going to integrate it. And what I'm going to do is I'm going to do it in square brackets. Okay, so I'm going to say that it is a quarter x to the 4 using that basic integration formula on the formula sheet. Okay, and then we're going to do between 2 and -1. Now that I've integrated, I need to substitute my b and my a. So this is b, this is a. Okay, so I need to do big F of b minus big F of a. And that can be done by going a quarter 2 to the 4 minus a quarter minus 1 to the 4. Okay, a quarter times 2 to the 4 is 4 minus a half. Okay, so that's equal to 3.5. That's the integral between -1 and 2. Okay, now the question is to find the area bound between x-axis and -1 and 2. So whenever we get an area kind of question, it's super important that we understand what the curve looks like. And how can we do that? By drawing what the curve actually looks like. So it doesn't need to look beautiful. Okay, and we're just going to go like this. Oops, that was really ugly. Okay, so everything's wacky off, but that's fine. We're just going to pretend that this is 2 and this is -1. Okay, so you can see that we have an x-intercept at the origin. Okay, and if it's a bit more complex than this, because x cubed is a really nice one, then we first need to draw the graph. We need to use our graphing techniques and draw it out first. That's the first step that we need to do, okay? Okay, now we're going to first find the integral between, well, the absolute value of the integral between -1 and 0 of x cubed dx plus the integral between 0 and 2 of x cubed dx, okay? So it will be the absolute value of 1/4 x to the 4 between 0 and -1 plus 1/4 times x to the 4 between 0 and 2. So it will be 1/4 times 0 minus 1/4 times 1 plus 1/4 times 2 to the 4 minus 0. Okay, put that together. So the absolute value of minus 1/4, so it's just 1/4, plus, what was this? It was 4. Okay, so it's 4.5. So you can see there is a bit of a difference, right, between just the integral and the area. Okay, if anyone has any questions on finding the area versus the integral, or anything at all, make sure you put it in the Q&A. Okay, let's move on to integration with symmetrical limits. Okay, so this is a bit of a shortcut when you're solving like symmetrical even functions, but also a bit of a giveaway when you have questions in like trials or the HSC where they only give you half of the function or half of the area, and they like ever so nicely mention that it's an even function. So if f of -x is equal to f of x, aka an even function, which by the way, another thing for you to memorize, even and odd functions, because that's not on the formula sheet and it's only year 11 content, which will rock up in the HSC. So let me just quickly do a straight. So that's even. And then f of -x is equal to minus f of x. That's odd, okay? Something that's important for you guys to memorize, okay? So yeah, if something is even and they only give you half of it, then between like even bounds, so between -a to a of like the integral is the same as 2 times the integral between 0 and a, okay? And inversely, if something is an odd function and you've got the same like absolute value of bounds, then the integral will be equal to 0, okay? Because the area won't be 0, but the integral will be 0. Keeping that in mind, because this will be the exact same value, just negative, and this will be the exact same value, just positive. Okay. Let me get myself to Q&A. Where did the 1 on 2 times, a half times 0 come from? A half time, oh sorry, that's 1/4 times 0. Apologies. But yeah, that's where it came from. It didn't come. Can you explain B again, please? Of course, I will explain B again. Okay, I'm going to assume that you're not asking about how to draw the graph. And we'll go through it all together. Okay, so because there's an intercept at x is equal to 0, I'm going to split it into two, where I have a negative thingy here and then a positive area here. So I'm going to do the absolute value of the integral between -1 and 0 of x cubed dx plus the integral between 0 and 2 of x cubed dx, okay? Now we're just going to split that into two. So it's going to be the absolute value of the integral between of x cubed, which is 1/4 x4, with those same bounds, plus 1/4 x to the 4 with the same bounds, okay? Now we're just going to expand everything. So it'll be the absolute value of 1/4 times 0 to the 4 minus 1/4 times -1 to the 4, okay? All under absolute values, plus 1/4 times 2 to the 4 minus 1/4 times 0, okay? So that gets me to the absolute value of 0 minus 1/4 plus 4, okay, minus 0. So that gets me to 1/4 plus 4. Oh my gosh, did I say? I'm so dumb. I'm so sorry. I put a half there, which is why you're probably wondering. Okay, so it's 4 1/4. And that is the final answer. I hope that helps. Okay, can you also slow down after each slide so that we have time to at least copy down if we are doing so? Absolutely, sorry. Okay. Okay, I'm hoping this is enough time. I'll give you guys a few seconds after each slide now. Okay, you can find the area bound between two curves by basically subtracting the two functions. So whichever one's on top is going to be the one that will be subtracted from, and the one that's in the bottom is the one that we're subtracting by. Okay, that sounds really weird, but basically, if we're doing the area bound between f of x and g of x, since f of x is at the top and g of x is at the bottom, we're basically going to find the area of f of x, which is all of that, and then we're going to find the area of g of x, and we're just going to subtract that out so that we're simply left with that dotted amount right over here. Okay, I'll give you guys, where did the quarter come from question B? The quarter came from question B, just over here. So 1/4 times -1 all to the 4, which is just 1/4, and then we're adding 1/4 plus 4, which is where we get the 4 1/4. Okay. Now let's go to a slider question. Okay, so find the area bounded between y is equal to x and y is equal to x squared between x is an element of 0 and 2. Now this one is a nice one, but upon further investigation, it's a little bit of a tricky one. That's my hint for you. Y is 0 minus 1/4 and not -3/4. The reason why it's not -3/4 is because we're just timesing the quarter over here, right? And because we're subbing in just -1, so it's a quarter times -1 to the power 4. So a quarter times 1. So there's no 3 in there. I hope that makes sense. Okay, I'll give you guys like 4 or so minutes to do this question. You guys can take your time. If you need more, then you can take more time. Okay, sorry, I meant where did a quarter come from on the second line of working? In this line of working? Yes, of course. So if you remember just from the original integration formula, we increase the power by 1, and that new power we also put in the like denominator. So x to the 4 on 4, aka a quarter times x to the 4. Okay, that's how it comes. So just like how we differentiate, we bring the power to the front and then subtract by 1. We just do the complete inverse when it comes to the integration, which is why we have the quarter over here instead of 3/4. Okay, so we don't take the 3 down to the bottom. Cool, we have 3 responses so far. Oh, sorry, I'm not even showing the question. Let me go back. Sorry. Okay, so we've got just a few responses. I'll give you guys a couple more minutes to figure this one out then. I think we'll aim for like maybe 10 responses or something, and then I'll start going through. Okay, let's get started. So currently we've got a wide range of answers. Let's get into the working. Okay, now my little hint that I had before was just that there's a bit of a weird thing going on, which we'll go through right now. Okay, so this is what a Cartesian plane looks like. Sorry, let me draw it up. Oops. Okay, so y is equal to x. Looks like this. Okay, and then we have y is equal to x squared. I'll do in blue. Okay, don't worry about the left-hand side. It looks a bit ugly, but there's a super small amount that's like being bounded by the two curves, aka between like where the two intersections are. So just here. Okay? And then there's 1, so between 0 and 1, and then we switch it when it comes to between 1 and 2. So we're going to make this come here and then over here. Okay, so between 0 and 1, the curve that's on the top is just y is equal to x. Okay, so what we do is integral between 0 and 1 is x minus x squared dx. Okay, and then we need to add the integral between 1 and 2, which goes the opposite. So it's x squared minus x. Okay. All right, now we're just going to integrate. So it's going to be a half x squared using our integration minus a third x cubed between 1 and 0 plus a third x cubed minus a half x squared between 2 and 1. Okay, now we're just going to sub everything in. So it's going to be a half times 1 minus a third minus 0 plus a third times 2 cubed minus a half times 2 squared, okay, minus a third minus a half. Okay, now we're going to throw that all into our lovely calculators. So a half minus a third plus 8 3 minus 2 minus a third, oops, plus half, which gets us to 1 unit squared. And that is the final answer. Okay. If anyone has any questions. Can you please explain the concept with the formulas for integration again, please? Absolutely. So just using this example alone, so let's do x squared. So I need to find the integral of x squared. Okay, so just the general rule for the integral of any x to the n is that we're going to increase that power by 1. So it'll be equal to x to the 3, or 2 plus 1. And then we're going to divide that whole number by that new power. So 2 plus 1. Okay? And then we're going to add plus c. So it's going to be a third x cubed plus c. Okay? So that's the general rule for integration. I hope that helps. Let me know if you need some more help though. Okay, now let's move on to definite integrals where we don't know how to actually integrate, or we're not given a proper equation. Now this can be done using something called the trapezoidal rule. It is, for a lot of people, the bane of many people's existence. In the question of the area bound by x and x squared, where did the minus a third minus a half come from in the end of the second last line of working? Over here. Yes, so that's minus, so we're doing like, we sub in the upper bounds and then we minus the lower bounds, right? So it's minus, we're just subbing 1 in, so a third times 1 minus a half times 1, which is where I got that from. Why did you subtract 0 and a third minus a half from fx and gf in the previous question? The reason why I subtracted a third and 0 is because in this case, I am doing the x minus the x squared. So if I'm just subbing in 1 first, then it's a half times 1 minus a third times 1, and then minus a half times 0 minus a third times 0, so it's all just 0. And then same happens on this side, but in the opposite direction because I've changed the direction. Okay, so for the trapezoidal rule, this is the general equation for a trapezium, which I think most of us would know by heart now, and I think it's in the formula sheet as well. Yeah, it is. But the trapezoidal rule can be used to find out the area bound by 2 places, okay? Just like so. And the trapezoidal rule is really disgusting. It looks like this, okay? And that can be found on page 3 of your formula sheet at the very bottom right corner, okay? That looks really gross, but another way that you can rewrite it, which is the way that I personally remember it, is the area bound for f of x between a and b is approximately equal to h, aka like b minus a, all on 2n. I don't like the way that's written. I'm going to rewrite that. ba f of x dx equals b minus a on 2n, first plus last plus 2 times middles. Okay, so that is the trapezoidal rule. Okay, now there is no question on this, and I want a question to be on this, so I'm going to make one up. So let's say I've got a river, okay, a dam, and the dam looks a little something like this, okay? So I have made a few measurements, okay? And I want to approximate the area of this lake, dam, whatever you want to call it, using trapeziums, or using the trapezoidal rule, okay? Like so. And the length from the wall for each reading is like 30, 35, 32, 28. Okay, so that is the whole thing. And now I need to draw out the trapezoidal rule. Okay, oh, and the length of my whole thing is, let's say 100 meters. Okay, so we're going to follow the whole thing. So b minus a on 2n is, well, if this is a and this is b, then b minus a is 100 on 2 times the number of subintervals. So I have 1, 2, 3, 4 subintervals times the first. So the first is over here and the last is over here. And coincidentally, they all have a height of 0. So 0 plus 0 plus 2 times the middles. So 30 plus 35 plus 32 plus 28. Okay? And that's going to be my area approximately. So it'll be equal to 100 on 8 times 2 times 30 plus 35 plus 32 plus 28. Oops. Which gets me to 3125 meters squared. Okay? Which checks out. Okay. Hopefully that makes sense. I'm just thinking whether I should continue into random variables. I think I might start. I'll literally only spend 5 minutes on it, and then you guys have access to all of the like questions and all my slides on the right. So whatever I don't finish, you guys can go through in your own time if you're interested. But yeah, as I was saying earlier, so year 11, we have like our discrete variables, our discrete probability, our discrete what's the actual word? I forget the word. But yeah, it's all discrete, all the variables. Then we come into year 12, where we've got continuous. Yeah, we can do another trapezoidal. I think that's more important. So yeah, we'll do another trapezoidal. Okay. This one I'll give you a few minutes to think about on your own first. So I'm going to do something pretty similar to this. So I have a fence, and then okay, this is what my fence looks like, and my fence is 50 meters in length. Actually, no, I want to do it a different way. Can I do it a different way? Nah. Okay, I'm just going to do it as an X. So if this is 20 meters from the origin, and this is 70 meters from the origin, okay, and pretend they're all really nice, and okay, and this is 10, 20, 15, 17, 17, 16, what? Oh, oops. 25, 40, 30, 30, 26, and 17. Okay, so I would like you to find the area bounded in this harbor bridge looking thing. Okay, so I'll give you a few minutes to do it on your own, and then I won't make a slider for this, but you guys can do it on your own. Okay, I'll give you another minute to go on your own and then I'll get started. Okay, let's get started. So let's just get all our variables intact. So B over here is 80. A over here is 20. And we got 2 is 2. And n is the number of sub-intervals, okay? So it's not the number of intervals, but the number of sub-intervals, which is a bit annoying. Intervals is just how many there are. So 1, 2, 3, 4, 5, 6. But 6, unfortunately, isn't the answer. It's the number of lines in between the intervals. So 1, 2, 3, 4, 5. Okay? Yeah. And now we're going to go f of a. So the length at A is 10, plus the length at B, which is 17, plus 2 times the middles. So 20 plus 25 plus 30 plus 30 plus 26. Okay, and we're going to chuck that all into our calculator. Okay, and that gets me 1,734 meters squared. Okay. We have a question. Okay, cool. Now with the final 9 minutes, I'll just go through some final study tips. Okay, so I don't know how many times I need to say it. Maths is a skills-based subject. Okay, so I know there are a lot of people that make study notes. Some people study notes works best, but for most people, as it's a skill-based subject, it takes practice, consolidation, and application to really thrive. Okay. The person that asked about the mistakes diary, that's one of the ways that we can keep track of and learn from all of your silly mistakes. If you're not keeping a mistakes diary, then you still need to go through that reflection of, oh no, I made a mistake. How did I make that mistake? Why did I make that mistake? Well, both together. What can I do that's going to prevent that the next time? Okay. Practice makes perfect. Perfect's a bit of a stretch, but practice makes near perfect at least. Past papers honestly are so good. THSC has so many from 2022, 2020, 2021. You might see a couple, but like a lot of us didn't have trial exams, so you won't see too many. And yeah, also understanding the rationale behind what you're doing. That could be the reason why you're sitting the HSC in the first place. What's your end goal in terms of the HSC, in terms of just your study session in general, even up to what's the end goal for this one question that I'm sitting right now. Okay. So tips for conquering your assessments: start early. The day that your assessment task comes in, go home that afternoon and analyze what's expected of you. For your assignments, get started on like a small plan or something. It really puts you a mile ahead of everyone else. Okay. Then breaking down what you need to do into specific actionable tasks. Okay, what's expected of you, and then what's the end goal? What can I do to get halfway? What can I get to do a quarter of it? And then all into small chunks. Once you've made it into small attainable tasks, you're so prepared to get everything done. because it's just so much more doable. Okay. Um, yeah, and okay, start and kick yourself into gear. Okay, so if you struggle with procrastination, I said that I don't get pro- get procrastinated with my phone, but I still get procrastinated. Like I still procrastinate with the smallest of things. I'll like just daze off into the window and everything. But something that helped for me was the Pomodoro technique. So 25 minutes of work followed by 15 minutes of break. Or if you it doesn't need to be that exact 25 and 5 ratio. It can be a bit longer or a bit shorter, just depending on like how you're doing. Limiting distractions. Currently, I do sometimes need to remove my phone from my room. Um, and just as importantly, committing to what you're doing. Okay. If you're going to do something, do it all the way with your full attention and get it done. I think it was someone today that was saying that they spend a lot of time doing their homework, and one of the reasons could be maybe because you're only not like you're not focusing 100% on the task at hand. Maybe, you've got your screaming siblings in the background and you've got your phone buzzing on your left hand side, which a lot of these things you can't have too much control over. But maybe going to the library or spending your study break studying instead of talking with your friends, just so you can get everything done faster and be more efficient. It makes such a big difference. Okay. um yeah, and the last takeaway, sometimes the biggest challenge of all, when doing something, is just getting started with it. So I don't know who needs to hear this, but you do not need to start your work at 3 o'clock on the dot or 4 o'clock on the dot. And if it's 4:01, then you most definitely can still start. It doesn't need to be a perfect number for the time that you start. Okay.